I welcome you all in this presentation related with the subject materials processing, fundamentals and practical. And we are talking about the metal casting. In this particular presentation, I will be talking about the die casting and sand mold casting with regard to the comparison between these two processes. So, we will see that what are the different factors based on which the two casting processes we can compare. Okay. One is the process comparison cooling conditions. So, because of the difference in the mold, the sand mold or the metallic mold. So, the kind of the cooling rates which are offered by the two types of the mold, that is significantly different, and that in turn brings in the lot of changes or lot of differences in terms of the like flow of the metal, the cooling conditions and the time to fill the cavity and lot of other things are affected. So, when the cooling rate is affected, so if the flow is fast, flow is slow, flow is it is taking too long time. So, this will be bringing lot of difference in the performance and the soundness of the casting. As far as the microstructure is concerned, if we see the microstructure and mechanical properties, since the sand mold casting, it experiences the molten metal during the solidification or cooling down after the solidification to the room temperature experiences very slow cooling rate, okay, slow cooling, while the metallic mold in case of the die, this experiences very high cooling rate, okay. So, slow cooling in general promotes the higher growth rate and low nucleation rate, and this in turn promotes the coarse grain structure. On the other hand, the higher cooling rate promotes the high growth rate, high nucleation rate and low growth rate, okay, and this combination causes the finer grain structure. So, this difference in the microstructure, what it causes, like the greater yield strength for the fine structure, yield strength is high, hardness is high. On the other hand, hardness is low and yield strength is low for the coarse grain structure. Okay. So, the mechanical properties, wear resistance, all those are significantly affected by the microstructure and so the mechanical properties. The another tendency is the defect formation, since the sand mold is made of sand, moisture, clay and binder and additives. Okay. So, these constituents behave in completely different way when they come in contact with the molten metal. So, interaction of the molten metal with these, the moisture with the clay, additives and sand. If there is anything improper, then what it will be doing? It will be promoting the defect. Okay. On the other hand, in the metallic mold, there is hardly any interaction. Interaction takes place so metal versus molten metal, metal of die and the molten metal. These interact, if these interact excessively, then soldering happens where the molten metal will be sticking the surface of the mold. Okay. So, this is one aspect where it is interacting, the molten metal is interacting with the constituents of the sand mold or with the metallic mold. On the other hand, the major difference in as far as the defect formation is concerned in the two cases come from the cooling rate. See, cooling rate, significant cooling rate being experienced by the molten metal in two cases. So, here slow cooling for sand mold casting, slow cooling, okay, and fast cooling for the metallic mold. Okay. So, here you see it affects the fluidity, time to fill the mold. These are the two very important aspects, okay, and the fluidity and time to fill the mold, both are affected significantly apart from the solidification time. If the solidification time is less or more, fluidity is less or more, or the time to fill the mold cavity is less or more. These things significantly affect the defect tendency formation in the during the casting by the sand mold or by the metallic mold or the die casting. Okay. As far as the productivity is concerned, that we can see in terms of the quality or the rejections. Okay. So, usually very good surface finish is obtained, very close control or the tolerance, less tolerance is observed, a very fine grain structure is observed, and good mechanical properties. Okay. And high production rate is observed with the die casting. Okay. With the die casting. But if we see this is particularly used for the, like say, the small to the medium size castings, a small to medium size, say 30-40 kg maximum, otherwise few grams to the 30-40 kg. On the other hand, the sand mold casting, the A is high, roughness is high, tolerance is also high. Okay. So, tolerance is also high, the grain structure is coarse, mechanical properties are lesser, poor mechanical properties. Okay. So, these are the things related to the sand mold, but as far as the soundness is concerned, that will depend upon the kind of the cooling conditions which are imposed or interaction of the molten metal with the sand is taking place. So, these are the various aspects about which we will try to look into the greater detail. So, the first and foremost important difference in the sand mold versus die casting is in terms of the cooling rate. So, since in the die casting we use the metallic dies which can be made of steel, cast iron or the brass, like that. So, when the molten metal touches the metallic surface of the die, the higher cooling rate is experienced, okay, depending upon the die metal or the volume of the mold or volume of the molten metal that will be cooled during the solidification. On the other hand, if the volume of the metal mold is very less, then the cooling rate will be very high. Okay. So, this another aspect is the sand mold casting. So, here the cooling rate experienced again like say 0.5 to the 50 K per second. Since the sand mold is of the lower thermal activity, it dissipates the heat slowly, and that is why very low cooling rate is observed during the sand mold casting. Again, there is a very wide range of the cooling rate that will be observed. Why? Because the volume of the casting will certainly affect the cooling rate. If it is being, if smaller volume means higher cooling rate, okay, and large volume of the casting means the low cooling rate, okay, cooling rate will be less. And the cooling rate, since cooling rate is extremely important in determining like how much time there is a superheat, say of say 50 degree centigrade or 100 degree centigrade. So, this will decide that cooling rate will decide that how much time it will take to commence the solidification, okay, to reach to the liquidus level. Okay. And so, if the cooling rate is very high, then heat will be extracted very rapidly, and then you see what will happen, higher cooling rate will be leading to the faster reduction in temperature. Okay. Fast, and that in turn will be increasing the surface tension and viscosity, that in turn will be reducing the fluidity. Reduced fluidity means it will be taking longer time, but in the case of the die casting, if we are taking very long time, then solidification of the casting in one of the sections may start. So, we may not able to afford that kind of situation. Okay. So, the filling time is needs to be very short for die casting, and it can be long for the sand mold casting. Solidification time accordingly will be affected. If the solidification time is very long, then we will be getting the coarse grain structure, and if it is short, then we will be getting the fine grain structure, especially when the no other solid phase change is taking place in the solid state. Okay. So, the cooling rate is single handedly responsible for the solidification time, and that in turn will be governing the kind of the grain structure that will be realized. So, the gas entrapment tendency is the another aspect that is affected by the cooling conditions. Okay. Say there is a mold in which a lot of gases have been dissolved. okay, like this. So, they are gases. So, if the solidification time is very less, then these gases will not get the enough time to float or to escape through the mold surface. So, that in turn, so high cooling rate especially in the die casting will promote the gas entrapment tendency, gas entrapment tendency. It is very important that there is a proper venting or the provision for removal of these gases. On the other hand, if we talk of the sand mold casting where the cooling rate is very low, then the gases will be rejected will be slowly. So, the rejection will be slow and the solidification time will be more. So, the gases will be able to escape from the molten metal and they will be able to diffuse out of the mold. That in turn will be reducing the gaseous defect formation tendency. Okay. So, this is the another aspect, the gas entrapment is affected by the kind of the casting method which is being used, mainly due to the difference in the solidification time. Metallurgical transformations in the liquid and solid state. So, this is very important, especially that will depend upon the kind of the metal system. So, the metals where there is no solid state transformation in terms of the phases, there the in the liquid state whatever the cooling conditions being imposed during the solidification, that will define the final grain structure. Whatever the grain structure is developed during the solidification, that will be final. Okay. So, if the cooling rate is slow cooling rate is imposed, then very coarse grain structure is achieved, and if it is high cooling rate is high, then certainly we will be getting the fine grain structure. But if there is a solid state transformation in terms of the phases like in most of the ferrous metals, then initially there will be austenite, then it will be transforming as per the cooling rate being experienced, it will be forming either coarse perlite, fine perlite, bainite, martensite and the perlite or only martensite. All that will depend upon the kind of cooling rate which is being imposed. Okay. So, the final microstructure as far as the metallurgical transformation is concerned, that will depend on both in the liquid to solid state transformation what is the cooling rate imposed, and accordingly we will be getting the fine grains or coarse grains. But if there is solid state transformation, then it will depend upon the cooling rate, okay, and the composition of the metal which is getting cooled during the casting. Now, as far as the defect formation tendency in the two processes is very different. You see, the sand mold casting and die casting, the defect formation kind of defects which are formed in the two kind of the processes are completely significantly different. Say, due to the high cooling rate imposed during the die casting, misrun tendency, cold shut formation tendency, alloys and the gaseous defect formation tendency and the soldering tendency. These are the common problems related with the die casting. Why? Because the cooling rate is very high, the fluidity is reduced. So, the misrun tendency, cold shut defect formation tendency and gaseous defect formation tendency because of the short solidification time and the interaction of the molten metal with the die surface, metallic die surface will be promoting the soldering. Okay. So, the kind of the defects which are formed in the die casting, these are the kind of defects, and in case of the sand mold casting, we know that there are many defects which are related with the poor sand properties, which are not really good for the casting purpose, say lower refractiveness, lower strength of the mold, okay, very coarse sand. So, those are other kind of defects. Additionally, if the filtering of the molten metal is poor, pouring temperature of the molten metal is low, then it will also promote the misrun cold shut kind of the defect. If the riser knot has been designed properly, then it will promote the shrinkage cavity. If the degassing has not been done, then it will also promote the gaseous defect formation tendency. But the segregation is one which is significant in case of the sand mold casting. Why? Because the solidification time is long. Whatever the impurities are there, they will be rejected into the molten metal during the solidification, and the alloy segregation tendency will also be increasing because of this slow cooling rate, and therefore, the segregation will be more in case of the sand mold casting as compared to the die casting. Why? Because In case of the die casting, rapid cooling will be causing the solidification very rapidly, may not be, this may not be leading to a situation where everything is getting rejected into the molten metal during the solidification due to the shorter time, and therefore segregation tendency is minimized. Okay. So, now we will be comparing these things with regard to the microstructure and mechanical properties for the die casting versus sand mold casting. So, die casting higher cooling rate will be resulting in the fine grain structure, for sand mold casting due to the low cooling rate will be resulting in the coarse grain structure. So, fine grain structure resulting in the higher strength as compared to the sand mold casting will be resulting in the lower strength, and the higher hardness of the die cast surfaces due to the fine grained structure caused by the higher cooling rate, this will be causing the greater adhesive wear resistance. Okay. On the other hand, lower hardness of the sand mold casting due to the coarser grain structure, this will be promoting the lesser adhesive wear resistance. So, adhesive wear resistance is completely different in the two cases. In homogeneity, you see, homogeneity is more, compositional and structural homogeneity is more in case of the die casting. This is particularly true due to the rapid cooling being observed in case of the die casting, and more segregation. So, increased segregation tendency and less structural homogeneity, okay, that will be there due to the slow cooling rate observed during the sand mold casting. Okay. Now, as far as the other aspects is concerned, for the die casting and for sand mold casting, if you see less hot tearing, why? Because our segregation is reduced in case of the die casting due to the short solidification time, and if the impurities are not getting segregated, then this will be reducing the hot cracking tendency. Okay. While the segregation tendency is more, means impurities, low melting point things, and they will be segregating more due to the longer solidification time, and therefore this will be promoting the hot tearing or hot cracking tendency. Okay. And then response to the heat treatment, heat treatment, it depends, although kind of the metal system, but say if it is about non-ferrous metals, T6 one of the common heat treatment, or in case of the ferrous metals it is austenitizing followed by imposing the suitable cooling rate, which may be like slow cooling, medium cooling or fast cooling, okay, for hardening, for normalizing or for annealing as per the case. In all these cases, what we want that the things are solutionized, okay, homogeneous austenitic state is realized, or the all alloying elements, all precipitates, all phases get dissolved even in the T6 treatment. So, what is needed? We need to heat the things to the high temperature so that the homogeneous solid solution is attained in both the cases. So, if we have the coarse grains, coarse precipitates, coarse phases, it will be taking longer time to form the homogeneous austenitic state or homogeneous solid solution state in case of the T6 treatment, and that long time will require the greater soaking time at a higher temperature followed by the desired cooling rates. Okay. So, if we have the fine grain structure, it is easier to break and dissolve, they will become unstable easily. So, our solutionizing time or austenitization time, that will be less. So, response of the heat treatment will be better as compared to the case when we are dealing with the coarse grain structure. If we are dealing with the coarse grain structure, it is going to take the coarse structure is going to take longer time or higher temperature to form the homogeneous solid solution followed by the desired cooling rate as per the kind of heat treatment to be performed. So, we know that for the T6 heat treatment, first is the solutionizing, then it is the quenching, and then it is aging. Okay. So, the solutionizing step takes very long if we have the coarse grain structure. So, that is attained in case of the sand mold casting, while the die casting will be resulting in the fine grain structure. So, our response to the heat treatment will be far better for the die cast components as compared to the case of the sand mold cast components. Okay. The same is true for your other the ferrous metals, like where austenitizing followed by imposing the different cooling rates as per the need. So, austenitization also take longer time for the coarse grain thing as compared to the fine grain constituents. Okay. Now, as far as the defect formation tendency in the case of the die casting and in case of the sand mold casting, that is also completely different. So, the defects may be in form of like the very rough surface or very large variation in the dimensions of the casting, or there are defects in the casting, large requirement for the machining. So, all that will depend upon the kind of the casting route which is being used. Okay. So, as I have said, the die casting offering the higher cooling rate, and that in turn reducing the fluidity and the time, reducing the time available for filling the mold cavity, and therefore, this will be promoting the defects like the cold shot, because the heat will be extracted very rapidly. Misrun, heat will be extracted very rapidly from the molten metal, and this will reduce the fluidity, and this will promote the cold shot and misrun kind of the tendency. Solidification time is also less, so the gases, dissolved gases will not have the enough time to escape. The flash at the parting line, say this is the die, okay, and here we have the casting, this is the another section, okay. So, if the dies are not held firmly, then and if the pressure being used to fill the mold cavity is very high, then what will happen, there will be tendency of the molten metal which is coming out at the parting line, and this will appear finally as a flash. Okay. So, when the casting is obtained in such cases where the little molten metal is coming out at the parting line due to the improper holding of the two parts of the mold, or the pressure is limited, or the pressure being used for injection of the molten metal into the die is very high, then that will promote this kind of the leakage at the parting line, and that in turn will be leading to the presence of the additional metal film or a fin at the parting line, and this needs to be removed. This you can term as a flash, this has to be removed. Okay. Since if the die has not been designed properly, then the metallic die certainly they will not allow much of the shrinkage. Therefore, there will be high tendency for the development of the tensile residual stresses, and if the metal is sensitive for the cracking, means it is having the wider solidification temperature range, then certainly this combination, especially in the die casting, will promote the hot tearing tendency. Okay. On the other hand, die soldering, say there is a metallic surface, metal, and over the metal surface we put the lubricant, and then we fill the molten metal. So, it is expected that the direct interfacing of the molten metal with the die surface will not be there, but if the lubrication is not proper or if it is insufficient, then molten metal can interact with the die metallic surface, and that in turn can cause the soldering of the molten metal with the surface of the die. Okay. This can make the ejection or removal of the casting from the die surface difficult. Okay. So, this can happen especially when the temperature of the molten metal is very high, or the lubrication being used is not proper, or the combination of the molten metal and the die surface is not proper. Okay. So, that will be promoting the die soldering tendency. The die casting is particularly preferred for relatively low melting temperature metals like the zinc, aluminum and magnesium, while the sand mold casting is preferred for both sand, ferrous and non-ferrous metals, large to the small size casting. So, this is die casting is mainly for the small to the medium size casting, okay. But the sand mold casting can be used for both, you see, a small to the very large size casting, okay. So, here injection pressure, if it is less, then the flow rate will be slow and it will be taking longer filling time, and that will promote the cold shut and misrun. Melt temperature is low, then this will again promote the cold shut and misrun. The venting is not proper, then this will promote the gaseous defects in the casting, especially in the case of the die casting. And the lubrication is not proper, then it will be promoting the die soldering, and die design will improper die design will be promoting the tensile residual stresses and increased cracking tendency. Okay. As far as the sand mold casting is concerned, because the sand particles are used, okay, sand particles certainly behave differently than the metallic surfaces. So, usually we get the rough surface. Surface roughness can vary, say, from 1 to 50 micrometer in terms of the RA also. So, very rough surfaces can be obtained, and because of the use of pattern, okay, and then the mold development. So, the kind of the variation in the size and the dimensions of the casting that is realized, that is there is a great variability, and because of that we get very high tolerance. The dimensional accuracy is very limited in case of the sand mold casting. So, rough surface means this will certainly require the secondary processing in form of the machining to achieve the desired dimensions as well as the desired surface finish. In the gaseous defect formation tendency is particularly encouraged if the moisture content is very high, or the binder and additives are creating lot of the fumes and the vapors due to the interaction with the molten metal, then those will be promoting the gaseous defects. At the same time, if the permeability related with the mold is also less, than that will be promoting the gaseous defects. Okay. So, the reasons, the causes for the gaseous defect in the two processes are completely different. Here gaseous defect in form of porosity in case of the die casting is observed due to the shorter solidification time. But on the other hand, gaseous defect in case of the sand mold casting are formed due to the excessive gas generation in form of the, like say, due to the moisture or due to the additives present in the binder, or the additives in the casting. Okay, and additives in the mold surface. So, if the roughness is more and the tolerance is high, then we need secondary machining to make the surfaces functional for the casting. And as I have already said, the sand mold casting suits for both ferrous as well as non-ferrous metals. Then as far as the productivity is concerned, the two processes are completely different in terms of the productivity. Why? Because the die uses the die can be used multiple times for multiple castings, okay, while the sand mold casting is used for the single casting. Okay. So, that since there is no loss of the die surface die casting or the die itself in the casting process, so same die can be used again and again for producing the multiple castings. Therefore, this allows very faster production rate as compared to the sand mold casting, because we have to prepare the sand mold each time after making the casting, it has to be broken. So, this is slow. Productivity, the rate of production that is observed with the sand mold casting is low. But you see that making the die is difficult, because this has to be designed and this has to be fabricated, and then it will be used multiple times. So, if there is if we have to use the die for producing thousands of the component, then this is justified, because the die design cannot be changed. If there is a change in design, then we have to make a new die. Okay. So, it is a costly affair, it is a time consuming, it takes lot of efforts to make the die. Okay. So, in case of the die casting, design change flexibility is not much, but in case of the sand mold casting, since the mold is being prepared for each product, so the product design can be changed very easily. So, there is a complete flexibility as far as the product design is concerned. So, the design flexibility is high in case of the sand mold casting as compared to the case of the die casting. Initial cost is very high in case of the die casting, and initial cost of the investment to be made in case of the sand mold casting is very low. As far as the production rate is concerned, very high production rate is realized with the die casting and very low production rate. Production rate is relatively low because the die mold has to be broken every time a new casting is to be after making the new cast, after making a casting. Then labor involvement, the sand mold casting is very labor intensive as compared to that of the die casting. Now, as far as the secondary processing requirement is concerned, because of the good surface finish and close control over dimensions, close control over the dimensions in case of the die casting, the secondary processing requirement is less. We get the good microstructure, good mechanical properties, good surface finish and close control over the dimensions. So, the secondary processing requirement is less, but for certain applications, if we require further closer control over the dimensions, further finer finish is needed, further refinement of the microstructure or better microstructure is needed, then certainly the machining or the post heat treatment of the casting can be done. Okay. The product complexity is concerned, die casting can be used for making the very complex shape products as compared to that of the sand mold casting. Sand mold casting can be used for simple to the complex, but if it is very complex, then the die casting is not used. Then the casting size from few grams to the few tons. The sand mold casting can be used for entire range of the size in terms of the size as well as weight. But as far as the die casting is concerned, this is limited to the small to the medium size, okay, from few grams to the say 40 to 50 kg size of the casting. So, here now I will summarize this presentation. In this presentation, basically I have talked about the various technological factors based on which we can compare the sand mold casting and the die casting, and how these differences result in the different characteristics of the casting produced by these two methods. Thank you for your attention.